This is how matrix transpose is usually introduced: swapping rows and columns or interchanging rows with columns. A matrix can be seen either as a collection of rows or as a collection of columns. A matrix transpose allows us to interchange the perspective from row perspective to column perspective and vice versa. With the transpose, we are treating the collection of operators or constant as collection of vectors or variables and vice versa. This is how a matrix will be interpreted if seen from different directions, symbolically. And the interpretation from each direction is equally valid, but with some different implicit assumptions. And instead of using notations which favor matrices from one direction, we will use the notation which favors all directions. This is how a matrix will be interpreted from two different directions with color coding. The question of translating one implicit assumption about matrices to another implicit assumption about matrices naturally arises, because we are free to choose any implicit assumption. For two different implicit assumptions to be equivalent, both must describe the same thing. A matrix symbolically seen and interpreted from two different opposite directions describes the same transformation. But is it true if a matrix is seen from two different directions which are not opposite to each other? The answer is not always. It suggests that vectors may be operators with some different implicit assumptions. In most cases of seeing matrix from two different directions which are not opposite to each other, we can treat vectors as operators and vice versa, but they won't describe the same transformation. And we can make operator space similar to vector space, but they won't describe the same transformation. Operators behave almost in the same way as vectors. We can add them, subtract them, and scale them. Also, we can transform operators in the same way as vectors. Here are some similarities between functions and numbers. And in the language of linear algebra, functions become operators and numbers become vectors. And just as we have I hat for basis vectors, we have I weight for basis operators. But PQRS aren't the only four directions from which a matrix can be seen. There are four more directions. This is the interpretation of matrix seen from R degree direction as compared to P direction. As you can notice, matrix seen from R degree direction is the transpose of matrix seen from P direction. This is an important conclusion, you can read it. R degree is the only perspective in which treating operators of P directions as vectors and vice versa describe the same transformation, which allow us to study the properties of operators by treating them as vectors. This is the reason why we will learn about matrix transpose from row matrices and column perspectives only in the next video. And we'll finally talk about duality. Remember, row matrix of P direction is column matrix of R degree direction and vice versa.